And I guess we'll go ahead and start by just talking about diprotic and triprotic acids and reviewing those. You probably remember that diprotic acids and triprotics are sort of the hardest part of Unit 1. There's a lot of different pH type problems that we can exploit. So I first have a titration here with a diprotic base, right? So this is the fully deprotonated form. Or when sodium dissociates, this is synonymous to A2 minus. And you may remember that the best way to approach any di or triprotic problem is to start with the fully protonated form, H2A. And I know that two protons can associate because there are two Ka values. And from there, you can simply write out all of the conjugate forms until you arrive at the fully deprotonated base, A2 minus. And that's going to give us this number line that we can use to visualize which species is major in each solution as a function of pH. So first of all, if you have a diprotic acid, you should think about pKa's instead of Ka's. Those are easier to visualize. So negative log of the Ka gives a pKa of 4 for the diprotic acid, and the monoprotic acid has a pKa 2 value of 9. And so now we can see that if the pH is below 4, major species is H2A. If the pH is exactly 4, then the equal amounts of di and monoprotic acids are present. And if the pH is anywhere between 4 and 9, then the major species is HA minus. Furthermore, at pH 9, these two are equal. Okay, so the way that you can describe that graphically is by drawing a fractional composition curve. And remember that alpha is the fraction. And the fraction is always going to be on the y-axis here, ranging from 0 to 1. And we're going to do it as a function of pH. So as we go from left to right, the pH is becoming increasingly more basic. And at very low pHs, we're going to have this diprotic form present to the greatest extent. And that will start out at approximately 100%, and it will decrease sigmoidally until it reaches a concentration of essentially 0. It will be this 50-50 mark that is very important for thinking about buffer solutions when we have half acid and half base. And I'll indicate here the HA minus in red. That will intersect with the H2A curve. At low pH, it hasn't formed yet, but as we start to deprotonate H2A, it's going to become HA minus, okay, and then that's going to furthermore decrease at high pH. The final form, A2 minus, is going to intersect with its conjugate species at 50-50. It will remain low in concentration until it becomes high concentration around pH 9. So remember that the intersection points here are the pKa's when you have 50% of each conjugate form. Those are the half equivalence pHs. Whenever you have approximately 100% of the intermediate, that's when the pH is the average of the pKa's, 6.5. Okay, that was like the isoelectric point. And if you think about each of these different forms, H2A is an acid only. So the acid just decreases with pH. HA minus is a base, is the conjugate base of H2A, but it's also an acid. And remember that that means the compound's amphiprotic. Or it can go both left and right. It's between pKa values. So that's why you have this parabolic shape here, where it increases at some pH values and then decreases at others. The final compound is just the base, A2 minus. That will infinitely increase until it reaches 100% at pH 11 or so. So you should always come back to this curve to think about what a reasonable estimation of the pH is for any of these diprotic acid-base problems. There's another curve that you should be able to draw, though. That other curve is a titration curve where the axes are different. Here we have pH on the dependent axis and mole equivalence of titrant, which is HCl on the independent axis. And I'm starting this reaction with the fully deprotonated A2 minus base. So that's going to start at a high pH, something far above 7. And it will decrease to a buffer region where it flattens out. That will reach an equivalence point, another buffer region, another equivalence point. So here, the equivalence points, recall, are when we have the inflection or the steepest part of the curve. At equivalence, the pH is changing most rapidly. The half equivalence points are when the curve is approximately flat, or where the change in pH is almost 0. And it is at these half equivalence points that we have a pH equal to a corresponding pKa. In this case, the higher pKa goes first because we're going from a basic to a more acidic solution. And then the second half equivalence point will give pH of 4. And remember that the best way to solve these problems is simply to think about where you're at on the curve. The first region is when you have A2 minus by itself, before you add any titrant at all. When that's just by itself in water, that's going to be a Ka1 ice table problem. Conversely, I guess we should better say this is Kb1 because it's a conjugate base. It's still an ice table whenever you have something weak by itself, though. Anywhere in this region here, it's a buffer. So in that region, we have some of A2 minus left over. We haven't fully titrated one equivalent yet, but we have titrated some of it, and we have some of its monoprotic acid present. And whenever you have a buffer, you're going to use the Henderson-Hasselbalch equation with the appropriate pKa of 9. So as long as you've added some acid, but not one full equivalent, you're working in the buffer region. At this equivalence point, the major species is now HA minus because we've titrated 100% of the A2 minus molecules to form the monoprotic acid. So it's basically by itself in water. And that's going to be an amphiprotic problem because it's both an acid and a base. We'll review that problem down the road. If you keep titrating with acid, then you're going to go into the second buffer region where the pH flattens out again. But now this buffer is a mixture of HA minus, some which has not been titrated yet, and then the final diprotic acid, H2A. So that one is going to be another buffer, but now we use the Henderson-Hasselbalch equation with the appropriate pKa of 4. And then finally, at the last equivalence point, all of your molecules have been fully titrated to H2A. And so that's by itself in water. And then it's just a weak acid problem, where you use the larger Ka value, Ka1, in an ice table. If you keep adding base, or acid, sorry, titrant period, if titrant is added beyond the final equivalence point, then it's going to give you some very acidic pH down here. And now we have excess strong acid. And that's when you're going to do simply a strong acid problem, where you ignore any weak analytes. So you ignore, for example, the weak acid. Okay, so if you can really understand this curve, right, then you can get an approximation for what your pH should be approximately. And I'll just go ahead and note that we can graphically see this first equivalence point pH should be about the average of 9 and 4, 6.5. And it's no coincidence we saw that earlier when you have HA minus by itself. Okay, so I'm going to go through and do some of these problems so you can recall how we actually solve for the exact pH mathematically. So the first problem we're going to solve is this one up here. Okay, and I'll keep these in the same colors so that we're adding no HCl at this point, and we just have A2 minus. Well, A2 minus is by itself, and recall that you have to react any weak analyte that's alone with the solvent water. And when two weak things react, it's an equilibrium arrow, where there will be an equilibrium constant, Kb1. And it will associate once, and that's what produces hydroxide. So the net production of hydroxide is what tells us that the pH is going to be basic. Whenever you have two weak analytes, we know that because of the equilibrium arrow, it's an equilibrium table. And in that equilibrium table, we must always use molarity. Because molarity, right, is the way that the equilibrium constant is defined, the concentration of products over reactants. We're told above that A2 minus is 100 mils, 0.1 molar. And we have not yet mixed that with anything. So it's still 0.1 molar, and you don't need to use the volume in this problem. Water is a liquid, and therefore it's negligible in the ice table. And you assume that you're starting from the exact instance where you put the base in water. So you have not yet formed any conjugate acid or hydroxide. Because it's weak, we only lose a small amount, where that X is much smaller than 0.1. And that's going to give you an equilibrium expression, where now we can say that the products that are aqueous over the reactant is equal to Kb1. So the only thing we have to do before we solve for X is to figure out the Kb value. And that will come from the pKa's. So go back above for that. So if you look at these pKa's here, this lower pKa, the more acidic one is pKa1, and the higher one is more pKa2. The most basic form is A2 minus. So that should have the highest Kb or the lowest pKb. And recall that pKb plus pKa add to give pKw 14. So if you subtract 9 from 14, you'll get 5 as being pKb1. And you'll get 10 as pKb2. So I have A2 minus as the base in this first problem. So I want to use that pKb of 5. So I'm going to say it's 10 to the negative pKb1. That's the way you get the antilog, or 10 to the negative 5. And on the exam, if you have a quadratic solver in your calculator, that's the most efficient way to do this and get the exact answer. But when this is so small, this is what, a 10,000th of the concentration, it's 4 orders of magnitude smaller, then you're going to get the same answer by just doing this representation. By saying that this is negligibly small relative to 0.1, because the equilibrium only shifts a tiny bit, right? This is 1 divided by 100,000. So you barely make any product. Furthermore, you can multiply over to show that x squared is approximately 10 to the negative 6. And therefore, x is the square root of that, or 10 to the negative 3, which says that the concentration of hydroxide, right, is 10 to the negative 3. So now that I know hydroxide, I can simply go and find the pH. So the pOH, right, is negative log of hydroxide, or negative log of x, which is going to be 3. And therefore, the pH is 14 minus that, or it's 11. And we knew it had to be higher than 9. So we can fill this in now. Okay, it's not going to be 9 until we get to that half equivalence point. So when you just have a weak base by itself, right, or a strong acid by itself, right, before the titration starts, it's just an ice table problem with the stronger equilibrium constant, in this case Kb1. Okay, so now let's start adding some titrant. And I've mentioned above that the titrant is 5 times more concentrated, 0.5 molar, okay? And we're still starting with this 100 mils of 0.1 molar base throughout. So we have 100 mils, I'm gonna use this equation now, so 100 mils of your base, it's 1/10 of a molar, and we're mixing it with 10 mils of HCl that came from a different source and was 5 times as concentrated. So remember, when you're mixing, the molarities change. Specifically, they go down. And you cannot rely on molarity anymore. So it's best to go ahead and calculate the moles or the millimoles. So multiplying 100, okay, times 0.1 will give you 10 millimoles of A2 minus, and 10 times 0.5, right, is 5 millimoles of HCl. So now we can do this table in millimoles, which does not change when we mix two things together. So if we add the dibasic form with a strong acid, it's going to give us protonation to give the mono acid and the chloride, monoprotic acid and chloride. And because now this is strong, it's a one-way arrow, which changes the table fundamentally from ICE to ICF. And in an ICF table, it's best to use moles or millimoles, because these are usually titration type problems where you are mixing and the molarities change. So I'll plug in the 10 and 5 millimoles into this table. Chloride is a weak conjugate base, so weak that it's negligible because it derives from a strong acid. And HA minus is not present yet, at least at the instance when we add the HCl, it's barely there. But this is a limiting reagent problem, and it will go irreversibly to completion until the smaller millimole reagent runs out. So you're left with 5 millimoles of A2 minus, none of HCl, and you make 5 millimoles of HA minus. And now we have two compounds that are conjugates of one another. Right, we have 5 millimoles of the monoprotic acid, and we have 5 millimoles of the monoprotic base. And what we saw is that the strong acid was the limiting reagent. Whenever that is true, it produces a buffer. If the strong titrant runs out and the two weak conjugates are still present, then you can simply find the pH with the Henderson-Hasselbalch equation. And I still want to use my first pKa, the one that corresponded to HA minus. Okay, doesn't matter if you're doing a weak base with a strong acid or the reverse, you use the same Henderson-Hasselbalch equation for any buffer. You always do the pKa of the acid plus the log of the deprotonated form over the protonated form. And here it's just 9 plus the log of 1. The log of 1 is 0, and so the pH is exactly 9. And so this is the half equivalence point. Specifically the first half equivalence point. The best buffer, or has the highest buffering capacity, which means it's the most resistant to pH change at this pH. And that's why the curve looks like it does. Right here at pH 9, right, we are at the half equivalence point, and we have equal amounts of these two, and the pH is barely changing. Right, the slope of that curve is quite small. So that's a buffer problem. Now that's perfect half equivalence point, but you can use the buffer anywhere in that blue region, right? And I mean, on the exam, if it's free response, which I guess it's not, but if it were, you would want to report to 2 decimal places for these. So 9.00 and 11.00. Okay. So what about after 20 mils of HCl is added? So now we're doubling our amount of HCl. Okay. So we still have our 10 millimoles of base. We're starting back from the beginning, right? Think backwards from 0. Now with 20 mils of HCl that comes from a 0.5 molar stock solution, multiplying those also gives 10 millimoles of HCl. In other words, they are equal here. So A2 minus is going to react irreversibly with HCl to give HA minus and chloride again. Same reaction. It's irreversible because of a strong acid. But this time, we change the millimole values. Now we have no limiting reagent, which means that the reaction goes to actual completion, and we only have 10 millimoles of HA minus produced. So we have HA minus alone in solution. So you should recall that that is amphiprotic. And an amphiprotic species is both acidic and basic, which means it's going to react with water. It's alone in water, and it's going to do two separate reactions. They're both equilibrium reactions because it's a weak acid and a weak base with water. One of them will be a Ka, specifically Ka2, which was 10 to the negative 9. If it acts as an acid, it's going to produce A2 minus and give up hydronium. That is decreasing the pH. If it acts as a base and takes a second proton and becomes H2A, that's going to be Kb2, which is 10 to the negative 10, right? We found that above at the very top of page 1. And then it would take a proton to become H2A and produce hydroxide, increasing the pH. So it's going to be some balancing act of these two pH changes, okay? So these are counterbalancing one another. And therefore, we have to be able to consider both equilibrium constants. Now you should think first, right, which equilibrium constant is more product favored? So what I see here is that Ka2, right, is greater than Kb2. So that means that the hydronium is greater in concentration than hydroxide. Right, it's making more product if the Ka is larger than the Kb. You're making more of this side, which means the pH should be less than 7. The way that you do that is by using a very simple PI equation. When you have an amphiprotic species alone, by itself, it's always the average of the pKa's that best predicts the pH. And remember, this is an approximation of the true amphiprotic equation or the isoionic equation, but it's quite close. So you're going to get 6.5. And that agrees with our prediction that the pH should be less than 7. And so now you can go back up here and see that on the titration curve, right? At this equivalence point, when we have HA minus an amphiprotic species, the pH is exactly 6.5, right? In other words, that half equivalence point, before and after, those can just be averaged to give any equivalence point between them. Now that only works for equivalence points that are between two half equivalencies. Okay, we won't be able to do that for the final equivalence point. Let's see, there's a question here. So the question is, would we do the same averaging of the pKa's if the hydroxide concentration is greater? And yes, you would. Okay, so no matter if the Ka is bigger or the Kb is bigger, no matter what this relationship is here, you'll always average the two pKa's if you have an amphiprotic species by itself. I just wanted to show you this rationale so we could have an idea for what our pH should be relative to 7, and that allows you to double check your math. A good question. Okay. So now at the second equivalence point. Well, to get to the first equivalence point, it took 20. So to get to the second equivalence point, that means it's going to take 40 mils of our 0.5 molar HCl. And I'm still working with my 100 mils of 0.1 molar A2 minus. Okay, 40 times 0.5 will give you 20 millimoles of HCl. 10 times 0.1, we're still working with the same amount, 10 millimoles of A2 minus. So now, writing the same reaction is going to give an irreversible, because strong acid, formation of HA minus. And we still have an ICF table with millimoles. But now the initial amounts have changed. We have 10 millimoles of A2 minus and 20 millimoles of HCl. And we're thinking back from 0 again, where we lose this time, for this first time, the weak base as a limiting reagent. And we have 10 millimoles excess of HCl, and we make the same amount of the monoprotic acid. So now we have two things present. We have a strong acid that is going to continue to protonate anything in the solution that is the least bit basic. It will protonate it. And we have an amphiprotic species, which means there's an option here. It could be an acid or it could be a base. And in water, it does both, because water is not strongly acidic or basic, so it does not cause the amphiprotic species to act a certain way. But when a strong acid is present, we are going to see that the amphiprotic species will react with the strong acid and act. In other words, if there's anything basic in solution, keep using your strong acid until you run out, and you write another equation here. Where now we're getting the diprotic form and negligible chloride. Okay, so same type of table, it's still irreversible because of the strong acid. And we have 10 millimoles of each of these after the first reaction, right? The final amounts in the first table become the initial amounts down below. And there's no limiting reagent, which means we're at an equivalence point. And therefore, we just have one species, and that is the product, H2A, that is present in a 10 millimole value or amount. All right, so that means we got to figure out a new way to solve this problem, because we have not had a problem so far where we just have H2A by itself. It's not a buffer, because this is gone. The conjugate is not there anymore. So in going from the first to second equivalence point, we skip the second buffer region in this problem. The reason it's not a buffer is because there's 0 of the conjugate form. So now we have a weak acid alone. And you should think, well, that's acidic. It's going to protonate something. And the only thing that's basic in solution is going to be water. So I got to write another reaction. I'm going to create some more room here. And I'm going to put that reaction up here. So now H2A is alone. It reacts with water. They are both weak this time, and therefore it's with an equilibrium constant of Ka1, which is 10 to the negative 5, or 10 to the negative 4. Okay, that's 10 to the negative Ka1. It gives the monoprotic acid H2A and hydronium. And this is not an ICF table, right? This is an ICE table now, where we must do equilibrium problems in molarity. Okay, let me clean that up. So we have the millimole value down here, but we need to do molarity. And currently the concentration of H2A is equal to the millimoles of H2A divided by the milliliters of solution. And the milliliters of solution is a total of 140. Because you started with 100, and it took 20 to get to the first equivalence point, so it takes 40 to get to the second equivalence point. And these are immiscible, or they are miscible, but they cannot be separated, right? Once you mix the volumes in titration, you're stuck with that whole solution. You can't separate the volume back out. So it's 10 over 140. And I'm just going to write that as 1 over 14. I don't care to plug that into the calculator. The liquid water, right, is negligible in the ice table. And we are starting at the instance where we have 0 of these. Okay, so we're saying there's 0, 0. So what we're proving is really this reaction can go backwards a little bit here, right? We're just going to give that proton back to water. Small amount reacts. Now you can set up an equilibrium expression where x squared over 1/14 minus x is equal to Ka1. And that's equal to 10 to the negative 4. Once again, 10 to the negative 4 is way smaller. It's 1,000th of 1 over 14. So I'm going to say, especially on a multiple choice exam, you can approximate this as x squared over 1 over 14 is equal to 10 to the negative 4. Okay, and then we'll plug that one in and take the square root. And for x, I'm getting 2.7 times 10 to the negative 3 molar. And the meaning of x in this case is the hydronium concentration. And so the pH is equal to negative log of x, which is 2.57. So that's at your second equivalence point. It is just a weak acid problem there. So let me go back up to the initial curve and show you this pH. Okay, there's a question. How can you make sure you use the right Ka? Good question. So I'm going to go down here and rewrite the equilibria to explain that. So whenever you're deciding which equilibrium constant to use in these ice tables, you should always refer back to this initial equilibria that we made. We had pKa1 was 4, pKa2 was 9. So if you have an acid, you're going to use one of these. And here we have the acid H2A. So in this solution, the major species that we have is H2A, and when it dissociates, it's going to dissociate into HA minus. So I find those two in my equilibrium, and then I use the pKa value between them. And then therefore the Ka1 that you should use is 10 to the negative 4. Okay, the HA minus could dissociate, but its pKa is 5 units higher, so it's very unlikely for that to affect the pH. Okay, so if you have two acids present, like H2A and HA minus, you use the lower pKa. But you always write out your equation, and then you determine which two species do I have, and use the equilibrium constant between them. Okay, I know it's going to be a Ka because I have hydronium in the equation. If you had hydroxide in the equation, then you would use the Kb that's between those two. Okay. So then finally, after 45 mils of HCl is added. So it took 40 to get to the equivalence point, which means this is going to be beyond the second equivalence point. Okay, so let me write out some similar equations here. If we start now with 45 mils of HCl, and it is, what, 0.5 molar, that's going to give us 25 millimoles, or no, 22.5 millimoles. Okay, so I'm going to rewrite the same equations, start from the beginning again, just so you can see it all. So A2 minus and HCl. Those are going to react to give the monoprotic acid and chloride. Irreversible ICF. We still had 10 millimoles here. We have 22.5 of HCl. So limiting reagent is the weak base. We have 12.5 left for HCl, and we make 10 of HA minus. That is amphiprotic. And because it's both an acid and a base, it can react with the strong acid present. So it can react with HA minus, again, to become H2A, the second titration equation. All right, you keep using this HCl until it runs out. So now the weak base is limiting, and you have none of it, and you produce 10 millimoles of the diprotic acid, and you only have 2.5 millimoles remaining of HCl. So this is after all the strong titration reactions go to completion. All right, so now you have two acids present. All right, you have a weak acid with a Ka value of 10 to the negative 4, which means that for every one hydronium, it took 10 to the 4. It takes 10,000 H2A molecules, right, to make one hydronium. That's a pretty weak acid. But then we also have a strong acid, HCl. And they're not going to react together, right, because there are two acids. But this one makes a hydronium for every single HCl present, right? It completely dissociates. So whenever you have a weak acid and a strong acid, I don't care what the relative amounts are, right? I don't care that this one is 4 times as concentrated compared to the HCl. You ignore completely ignore the weak one, and you just think about it as a strong acid problem, where you know the pH is going to be negative log of the excess HCl concentration, because it totally apart. And therefore the pH is equal to the negative log of the 2.5 extra millimoles of HCl divided by the entire volume. V total after mixing to this point is 145 mils. And that will give you the new accurate molarity after dilution and the final pH. So I get 1.75. And it should be quite acidic. And you add a couple more drops of HCl and it just shoots down to 0 basically. So after that equivalence point, the pH really is influenced strongly by the excess, that extra drop or two of your strong acid. So I'll go back here and label that on the curve somewhere down here. You have like 1.75. Okay. Okay, so that's a titration of a weak base with a strong acid, but we can also do the reverse, okay? And on the exam, you could be asked either direction. So you want to be able to do those starting with a weak base and starting with a weak acid, or going up or down in pH, okay?